It's a great pleasure to be here today in Brussels. My name is Bernstein. I'm a faculty member at the University of Zurich in the Department of Informatics. Before coming to Zurich, I was on the faculty at NYU. I did a PhD in the United States and grew up in my fair own city in Zurich. So it's a pleasure to be here. And thank you, Francis, for inviting me and getting me here to talk about a topic and subject that I've been looking at for the last 2 years or 3 years, and it's very close to my heart. The topic I want to talk about today is programming the global brain. How can we implement programs that we can use to run on the system that we call the global brain? Now, my understanding of the global brain and the one that's predominant here may not be precisely the same, so let me first of all tell you what I think the global brain is, at least in the context of this work, and then we can maybe tell you what I mean with programming the global brain. So the internet has changed the way people and machine collaborate with each other. Before the internet, people were mostly working with other people that were closely to them, and with the internet it's essentially possible to collaborate with everybody anywhere in the world at almost any given point in time, assuming they're just awake at this moment. So the result is these encompassing networks that go around all the world. In 1996, Tom Malone and Jack Rockert, 95, published a paper in Scientific American where they said what could be the likely effects of this massive fall of communication cost. And they came into 3 effects that they were seeing. First level effects, second level effects, and third level effects. And I think they underlie a lot of what these developments are. The first level is that we should see a substitution of information technology or computer-mediated communication for human communication. All of us are old enough that we've still seen movies where this thing happens, right? We have human people essentially playing switches, but arguably generations today don't know this anymore, right? I mean, today, I'm calling up a person, I'm telling them to whom I want to be connected with, doesn't exist. I guess we in our young days all played games about collect calls that we agreed with our parents. I'm going to travel there, I'm going to ask for a collect call with you, and you're going to reject it, and you know I'm arrived well. That is one thing we gamed the system. My daughter just told me a story that she went to camp, and the kids were not allowed to bring their cell phones, school regulations, because there was a payphone in the cellar, and so one of the students went down and was trying to make a phone call home that everything's fine, and he went back to the teacher and said, the phone is broken. And he said, what do you mean the phone is broken? He's like, I pushed the buttons of the numbers, but nothing happened. And it was an old phone dial, because those dials were put in place to essentially give impulses that would run the first mechanical switches. So the first prediction is we will replace communication, human communication, or human coordination with IT, with information technology, because it's cheaper. Well, given that it's cheaper, there is a second level effect. And the second level effect is that we will increase the overall amount of coordination used or communication used. Now, that's an obvious effect. We see this all the time. I mean, each of us runs around with about 4.5 communication devices at a given point in time. My students who come to class today, the first-year students who come to class today, probably carry around more computing powers that I was allowed to carry across the border into the East a couple of years ago, right? So that is just normal that we run around with it. So there is much more of this around. Now, the much more of this around actually enables the third level effect. And I think this third level effect is the interesting part. The third level effect is really this, that we can build communication-intensive structures. So structures that would not have been possible without massive use of coordination. Now, some of you are nodding, yeah, that's obvious, yeah, I've known this. But for those of you who may not think that's as obvious, let me give you an analogy from the Industrial Revolution that I actually think is a very interesting part. So the first level, or the first wave of the Industrial Revolution is the steam engine, as we've all learned, right? So it must be true because we've all learned it in school. It turns out there is an interesting secondary effect that came into place when electric engines replaced the steam engines. The first factories were all built around the the distribution of mechanical power, right? So there is the central water wheel or central steam engine, and the biggest problem was get the mechanical power to where the production happens. So you have these huge leather belts that went around the factory, and if you ever get to visit one of those factories, it's fascinating. It turns out that the whole production process in these factories was organized about optimal distribution of mechanical power. Now in comes the electric engine. The electric engine has the first level effect, it's cheaper and easier to maintain, so you throw out the old steam engine, you put in an electric engine, in exactly the same place, and you still use the leather belts. Well, as we all know, distributing electric power is much easier than distributing mechanical power. So suddenly, we can build these machines that independently have electric engines in it, and just, draw a cable to there. Which meant that the factories could be rebuilt by not having these these leather belts going everywhere, but you could actually put the machines there. Now that's the second level effect. The third level effect is that you could completely reorganize the factory along the production process rather than about the process of having to distribute mechanical power. And this is something similar that happens here. We can suddenly build our structures not around the need of efficient communication into human communication, but we can build completely different structures that optimize the process rather than the communication structure on the line. So this is one big thing that's happening. A second thing that I believe is very important actually takes place not here, but is first being established or seen in the court in Vienna around 200 to 300 years ago. So this, what you see here, is the mechanical Turk, and I don't know how much you know this. The mechanical Turk was a robot that in its heyday was the grand thing to use at the Vienna court. It will play chess, right? So there is this robot up here, and it will play chess, and it will win against most people at the Vienna court. Wait a minute. 200 years ago, robots? That shouldn't work. Actually, it didn't work. There was a short person, as it would be said in politically correct terms, who placed himself down here, and he played the chess for it. So this notion of the mechanical Turk, this thing that makes you believe that it is a human there, a machine there, but it's actually a human, starts this notion of human computation. Right? Humans are good computers. As a matter of fact, there is this famous ad from the New York Times about 200 years old that says computers wanted. They didn't want Apple computers. They wanted people. I think the monthly salary for a computer in the statistics office of the Federal Agency of Statistics at the time was about $4.15. So that at the time was apparently a lot of money, or sufficient amount of money to draw people to apply for the job. Now, human computations has completely different feature than machine computation. For all of you in this room, it is possible to see the outliers on this chart in constant time. Right? It's a look, and you know what the outliers are. Why is a good question. It's a question of evolution. Apparently, it's important to find outliers and very, very quickly to decide whether the thing that's walking towards you is something that you can eat or something that eats you. So, run or catch it, right? This is apparently something that was important, so we developed these structures to do this. For machines, this is complicated. And this is, the complexity of this task, the question whether you want to do this precisely or not, is at least somewhere in the polynomial range. God knows, some of you may know this better than me, but it's not constant time. It's much slower than constant time. Now this notion has been exploited on the internet, or has been started to be exploited. There's this tool called Amazon Mechanical Turk, where you can post your tasks, and people will decide whether this is a male or a female picture, and things like that. And you can do this. Another example for this is this beauty here. It's a Galaxy Zoo put together by some people. So essentially what you can do is you can classify galaxy, right? So you look at these images, I believe they're from the Hubble telescope, and you can say, is this a round galaxy, a spiral galaxy, etc.? And there is kind of a decision tree that is a couple of levels deep, and it helps these astrophysicists do their tasks. And it turns out, interestingly enough, that some of these amateurs are much better at doing these things than people with PhDs in astrophysics. Because the cognitive capability does not necessarily correlate with a desire to get a PhD in astrophysics. Okay? So that's one thing that's very interesting. This is another beautiful human computation task, reCAPTCHA, because it actually does human computation on multiple levels, right? So you've seen these multiple times when you try to log in on websites or get an account. What you're asked to do here is to take these two sets of letters and type them in here. And what you're really doing is you're doing OCR, optical character recognition for Google. What you're also doing is you're exploiting the fact that humans are good at this and machines are not, in order for whoever wants to use this as a differentiator, whether you're really a person who wants to get into this website or not. Now, how do you crack these? It's a very simple way to crack these. You set up a website where you offer people pictures of things that they want to see. And then those people, in order to see the next picture, you give them one of these CAPTCHAs and they will type them in. Now, obviously, oftentimes those are websites where you see a lot of skin, and I'll leave the rest to your imagination. And those are ways that people get around these CAPTCHAs. So there is human computations happening on two levels, right? So there's human computation happening in order for people to do OCR, that's the originally intended task. And there's a second level of human computation that's being abused in order to, to beat the system that was the human computation was put in the first place. Okay, so we have two effects now. Communication is cheaper, much cheaper, and allows coordination, more coordination-intensive structure. And the second one is this notion of human computation. Let me give you a third one, which is social computation. So this is the idea that it's not just individuals that can do computation, but whole groups can do some kind of computation, which gives rise to this notion of collective intelligence. I'm sure there are specialists in this room who know much more about this than I do, but it is an interesting notion that you can build structures where the intelligence lies within the structures or within the in the metaphors or within the rules that these structures use, and intelligent behavior arises. So people have started to study this a long, long time ago, if you want to say so. The whole area of business administration, organization science is nothing else but an endeavor of how to build social intelligence systems in some way. There have been interesting outcomes lately. For example, how can you measure the intelligence of a social system? And some people at MIT, CMU, and some other universities in the US, for example, have developed something that they call a social intelligence test, an intelligence test for the group. And one interesting finding that they found is that the best predictor for the intelligence of a group is not the average intelligence of the group, people in the group, or the best intelligence, the highest intelligence, but the fraction of women in the group. Women in the group. So we are not a very intelligent bunch of people here, right? Because we have only 2 ladies in the room. So we should make sure that this changes. Now, ladies, as much as I'd like to support your ego, it's not the fact that you're women that makes you good at this, but it's the fact that you're good on the Barone-Cohen test. It's a test that shows you just kind of the eyes, and it then lets you kind of make a judgment call as to what is the internal emotional state of the person. And apparently women are much, much better than men at this test, and therefore that is essentially apparently an activity that helps in developing intelligent teams that as a group perform very well on a bunch of tests. Okay, so if we take those 3 effects together, we have something new. If we summarize those 3 things, you get a set of unprecedented possibilities. What we can do with these unprecedented capabilities is build new global systems like the global brain that combine the the cognitive capabilities of people with the number crunching capabilities of machine to essentially deal with problems that were before not possible to deal with. So you have these networks of people and these networks of machines, and you can interleave them to build new stuff. Okay, so much about what my generalized idea is of what this global brain is. So what can we do with these, right? So what are examples? Let me just give you a few examples to kind of set the stage before we go into this. So we've seen galaxies, etc., but there are others, right? I don't know how much you know about the Netflix prize. This was a challenge put out by Netflix, which are those people who have this online video viewing thingy, where the biggest problem they have is actually making sure that you always have a full wish list of things you want to see. Otherwise, you cancel the subscription to watching this kind of special video on demand channel. So they put out this price and said anybody who improves our current performance by more than 10% will get $1 million. Okay? People started to collaborating on solving this problem. And sure enough, lo and behold, the team at AT&T Research won the Netflix prize. They had to do some changes on the way. They had to put in some intermediate prices because people got tired. It was a very hard problem, right? They had tasked a number of professional companies in this recommendation area to solve the problem, and they couldn't do it. So they had to put in intermediate goals, etc. But fact is, their problem was solved, and Netflix is on the record to say that they probably got 10 times the amount of research out of this than they put it out as a price, right? So this seems to be a good example. If you want to develop some of your own code, there is this website called Top Coder. You essentially put together a competition in coding. You all know crowdfunding sites, etc. And so forth. So those are all good examples where you only coordinate by machines, but there is also kind of the opposite, where the humans are essentially the foot people, and the machine coordinates. Let me just give you one example. This is a wonderful work from some people out at the University of Washington, where what they take is they take lots and lots of photos from Flickr. This is the Piazza San Marco, and what they do is they compute the conglomerate 3D model of the piazza. So this is just humans as sensor on vacation, taking photos, and you combine it into a 3D model. I mean, this is amazing. It just shows you that if you have a machine coordinator, machine contributors, and human contributors, you might combine them. Okay? Now, as the harbinger of good news, I need to be the harbinger of bad news as well. Collective intelligence is not just good. There are big mistakes that they do. This is one of the standard questions. It's a paper published in the Communications of the ACM in 2003. People asked their undergrads, did the 1999 Rambouillet Accord allow NATO to operate in all of Yugoslavia or only in Kosovo? It was a question that people were asked in undergraduate students in the US. So let me ask you, did the 1999 Rambouillet Accord allow NATO to operate in the whole of Yugoslavia or only in Kosovo? Who's in favor of the whole of Yugoslavia? Oh, this is a whole of Yugoslavia, only Kosovo. Okay, we have one vote against two votes. Okay, so it turns out they did these surveys. People usually Google this, right? And they went to the State Department website and saw all of Yugoslavia. The 1999 Rambouillet Accord actually do not allow to operate in whole of Yugoslavia. The NATO used this as an excuse to bomb Belgrade, but actually the accords do not allow to do this. Some people went to two sources. Some people went to NATO websites, and they got the right answer, and only very, very few students asked multiple sources. By the way, if you think those American undergraduate students, they are dumb, they don't know this, forget about this. I ran the same test in Zurich, so it's those stupid American and Swiss students, right? I challenge you to run the same experiment here in the class. Okay, here is another extremely famous failure of collective intelligence. This is the 1987 stock crash in the Dow Jones Industrial Average. I mean, markets are a collective intelligence institution that has been put out, and actually the people who've studied markets have always said this is a collective intelligence thing. It's kind of the collective setting of a price point for a resource, and it factors its scarceness, etc., etc., etc. I don't believe that on this one day the American economy lost more than a third of its value. It just can't be, right? And we all know today that that's not the reason. There's a whole bunch of reasons why this happened. So collective intelligence can fail pretty spectacularly. Okay? So we need to keep this in mind. So now I'm going to become the computer scientist that I am. The big question is, though, so what is different with those people and with the machines that just do what I tell them to do? And how can I take these differences into account to program them? Now, programming people is a politically extremely incorrect person, so let us say to coordinate and cultivate them to do what I want. Okay?
To nudge.
What? To nudge them. Oh, nudge them, right?
Mobilize them.
Yeah, I mean, we're in a city where a lot of politicians are trying to nudge us in the right direction, right? So okay, so I think there's three basic differentiations between people and machine. I'll just kind of go through them. There's probably many more, but there are three on which we focused in our work. The first one is a matter of motivational diversity. People are motivated differently than machines. Yes, there have been experiments underway ever since the 80s to essentially put up marketplaces for computation time. Some of the earliest work we talked about yesterday evening were happening at Park Xerox, But nonetheless, people are motivated differently than machines. So people are usually motivated by, money, fame, love, and what I would call side effects. You doing one thing and really you're doing something else. So Duolingo is an example of a perfect side effect. You're being enticed to learn a language, and the system helps you learn a language. What you really do is you do translations.
Machines are not motivated.
Machines are not, well, machines are motivated by electricity, I would argue, right? And you can just cut it off, but they won't start arguing with you, right? I mean, unless you're, where's this in I don't remember what the science fiction thing was, where you had to kind of convince the computer to do something. Oh, is it
2001 Space Odyssey?
2001, right? But that's a very good example where you actually couldn't motivate the machine, right? You had to unplug the RAM. I know there is is it Silent Running or Dark Star, one of those old movies where they're essentially arguing with the nuclear weapon why it shouldn't blow itself up, and they're going into this whole philosophical discussion. And at the end, the bomb takes this. These sentient bombs. The bomb takes that. I need to explode in order to make room for a new thing. And I'm sure there is some philosopher who said that's logical, etc. So we have very little of this. There is one programming language that I know of where if you tell the computer do X, it will say no, only if you ask nicely. But it's not your usual way to program machines. The second thing is we have enormous cognitive diversity in human people, right? So people can do different things well and not well. And trust me, I notice increasingly that the kinds of things I used to do well, I'm not doing that well anymore, and vice versa. So, I've recently started to take one of my courses, and it's a MOOC now, and so I've turned it into a flipped classroom setting. And trust me, it is very, very difficult for me to do some of the computations that I used to be able to do on the fly, because, the math labs of the world have just corrupted me. I'm just not used to it anymore. So my cognitive capability has changed. Could I become good again at doing my math on the blackboard? I might be able, but it's not active capability. It's definitely passive capability. Last but not least, we have a very wide variety of error diversity. Now, first of all, we're good and bad at some, not just good and bad in some things, but if you ask the same person in different situations, they're good and bad at this thing at different times or at different repetitions. You ask me, to look at an interesting data table, it's interesting, it's entertaining, I might give you some interesting insights. You ask me to look at 100,000 interesting data tables, I will, at the latest at the third table, I'm going to do a very bad job unless my life depends on it, right? So the error diversity is relatively high. You ask me at 6 o'clock in the morning, you ask me at 3 o'clock in the afternoon, you ask me just about having had a very healthy lunch at your cafeteria, my error diversity will fluctuate greatly, okay? So, in order to build this global brain, we not only need to understand how to program distributed systems, we need to how to program distributed systems that involve human actors that are complicated, right? They're not as nice as machines. They have motivational diversity, cognitive diversity, and error diversity. Note, societies exploit cognitive diversity in order to get better decisions. Arguably, democracy is one system that exploits cognitive diversity to get better decisions, right? Otherwise, and motivational diversity actually. Otherwise, let's just get a king, and the king will do the right thing. You guys have your experiences with kings, much more than we in Switzerland. We kicked out the Habsburgs in 1291 and haven't had them in Switzerland since. The Habsburg happens to be in Switzerland, and we're very happy without the Habsburgs. They merrily went off to Vienna and ruined another country. So, for a computer scientist, there's three questions. So if I'm to build this thing, what is a social operating system as opposed to a computer operating system? So, right. Secondly, what is a social programming language? So how would I go about specifying these things? And what are some of the requirements to such a language? And thirdly, what is social software engineering? Right? Because we want to do this in a principled way. We don't just want to go about and do the trial and error. Trial and error does not always lead to very good results. So let me focus on each of these three, and you will see I'm doing this very much out of the eyes of a socially aware computer scientist. Now, so social operating systems. I need to say that we are very well versed at building social operating systems. It's not something we've done for the first time. This is the American Constitution. It is a social operating system. Now, you could argue it's a good operating system or a bad operating system. I have to actually think it's quite a good social operating system because there was this Greek guy who rewrote the American Constitution to become the Swiss Constitution, which is heavily inspired by the American Constitution, so I have to like this Constitution almost. It turns out, that these things have led to quite a lot of wealth over a non-operating system environment where just the king was the absolute rule, right? I mean, we all benefit from the fact that these operating systems are around. So what are the requirements for these operating systems? In traditional operating systems, what they do for computer, they do things such as memory management, process management, I/O, input-output, what are the files, what are the printers, how do you control them, security, inter-process communications, how to do programs talk to each other, etc. A distributed operating system, if you have a whole bunch of computers, additionally worries about things such as transparency. How do you make a program unaware on what kind of computer that it runs? Heterogeneity. How do you deal with the fact that the representation of a number on one computer is different than, sorry, I'll stand over here so you can read, is different than on another computer? Failure handling. What are you going to do if a computer crashes? You can't just cache the world just because a computer crashed, right? You need to continue, so you need failure recording and scalability. How do you scale to really big problems? Okay? Now, what do we do with social operating systems? Well, the problems are kind of similar. We need to think, but we need to additionally think about motivation. How do you convince these people to do this, or some of these computers? Cognitive diversity, which is really, using a computer scientist term, this is heterogeneity plus. This is way more problematic and advantageous than heterogeneity, right? I have a supercomputer, I have my laptop, they both have very wide, cognitive capabilities. There are some programs that may run on supercomputers, there are some programs that may run on my laptop and vice versa. I don't want to build a rich user interface with a supercomputer. It's a pain. And it goes on. Identity management, relationship management, communication, social content distribution, coordination service, commerce, payment, etc., etc. There are all these problems that we need to solve. Now, I'm not going to offer you a finished solution. Otherwise, I would have my chopper waiting outside to take me back to my company later and would have come in with my private jet, etc. But what I'm doing as an academic, I'm going to try and just show you one possible problem and one possible solution that we've been researching and that we're looking at. And the problem that we're going to look at is motivational diversity. How can you bring motivational diversity into a social operating system, start dealing with it? Okay, so let's take a very simple task. The task is the following. You have these photos and you'd like to know who the heck those people on those photos are in your photo family album. Right? In your current setting, you'd have to go by the following task. You guess the price that it's worth it to do this as a human computation task. You post the task on Mechanical Turk, and you pray that it's going to be the right price, not too high because otherwise you overpaid, not too low because otherwise nobody will do it, and you hope that it's going to be done by the time you have your family reunion. That is really, really not what we computer scientists like, right? We computer scientists like press a button and things happen. Just like that for you. Okay, so crowdsourcing under time constraints are how can you deal with crowd latency. The crowd out there, they're not always around. As you may know, if you start browsing the internet, in the morning it's much faster, certain websites are much easier to access than in the afternoon, because those people in the US have woken up and are using the internet as well, right? And they're also putting load on these things. Quality management. So this is the cognitive diversity part, right? I mean, who do I ask? And error diversity, how good are they at it? And last but not least, how much should I pay them? I have no clue. How much is the task worth right now? If I want to, or how much is the task worth anytime between now and the end of the day? Amazon on EC2, which is their cloud computing service, has fixed prices and they have spot prices. You can buy spot service. And the spot prices fluctuate heavily depending on how many people have fixed units running on. And what we do in our research group is we developed a little script that if we have heavy computational tasks and we cannot run them on the machines in the university, we have a little job that we start and we tell it how cheap we would like the program to run, and it will just pull Amazon's current spot pricing, and if the pricing is low enough, it will start 1,000 instances at Amazon, run these, and turn them off again. Right? That's what you want. That's what you want, right? Now, how do you do this with people, not with machines? So, here's a task. Let's say you want to translate 10 pages from German to English, or Dutch to English if you prefer, since we're here at the VUB, within the next 20 minutes in good quality, as cheap as possible, but not for more than 10 bucks, because otherwise it's not worth it for you. Let's say you have this task. How do you do this? Now, there is some related work on this. There is this guy, it's not me, it's Michael Bernstein, not Abraham Bernstein at all, who essentially introduced this idea of a retainer model from the physical world into mechanical Turk. Right? So how about I pay you to hang around? And I'll pay you even more if you do a task for me. That's how I can allocate work resources, even though I don't know yet whether I will need them or not. So I'm essentially paying the option pricing for making sure work power is available. That's a kind of a base price. So you use a two-based payment for your workers. You pay the option that they're around, as well as some premium if they do the work. Rather than just do piecemeal, it's a two-piece payment mechanism. Singer proposed an online pricing mechanism that maximized the number of solved tasks under a given budget using some mechanism design-inspired approach. Okay. Now, what have we done? We've kind of said what we want is a system that incentivizes everybody to be truthful about how much they want to be paid for the task. So we need to build an economic mechanism that will entice people to actually tell them how much they want to be paid for this. Truthfully. So not inflated. Well, I don't think anybody will say too little in the hope to get the job. Well, maybe they will, but not on mechanical Turk. And we need to assess how good they're actually doing this, namely the crowd workers. So the process is the following, and I'll show you that in a little bit more detail in a minute. We ask people to pass a qualification test to be able to assess the quality of their work. Then we ask them to bid on tasks. You know, how much of these tasks would you like to do, and how much would you like to be paid per task? And then we allocate the tasks to the people and allocate the payment. So here is how we do this. We have this algorithm that does the following step. First, we run a procurement auction. A procurement auction is nothing else but a fancy word for saying we ask people for their bids. So these are the workers, right? So they get something that looks like this. We have some tasks. You need to translate, improve the sentence here. Please do this. And then they type it in here. This is the qualification test, right? A very simplified version. And then you ask them, so how many of these would you like to do, and what is the minimum wage you would like for each of these? Okay? So now we have the bids from the people. You're still going to ask me, why are those people not enticed to tell us 50 bucks, right? I mean, why should they be honest and truthful? That'll come in a minute. Okay. Step number 2, we need to decide, given this scheme of quality and pricing, what is the optimal way to give people the tasks, right? And what we propose here is a combinatorial optimization problem tasked as an integer program that combines the following things. First, we'd like to maximize social welfare. So this is, cost times task assignment, right? So this is the cost for each of the tasks, and this is the assignment for each of the actors I, and so this is what we're trying to maximize or minimize depending on what you're doing, right? I want to minimize the cost for me, so I want to have all the tasks assigned, all the xi need to be assigned, because otherwise I have a problem, so I can't have half of the work done or a part of the work done. There's a time constraint. I'd like to have the sum of these all be less, this fancy product here, done within a certain time frame, at a certain quality constraint. And there is this problem that tasks, there is this kind of fixed number of tasks. And there are no fractional tasks. I can't have half the task being done by and half the task by other. So what this algorithm does is allocate optimal chunks of things to an optimal chunk of people. Step 2 is, how do we decide how much to pay each of these people? And this is this thing down here. Now, there is this payout mechanism called Vickery-Clark-Groves. How many of you are aware of VCG? Okay. So this is Nobel Prize winning technology, you would argue. This is a payout mechanism that incents you to be truthful. And it works as follows. The payout mechanism tries to find an optimal payout that will pay each person at least the amount of money the person bid for, but if possible, more. And it determines the amount by the contribution, the value of the overall work done with your contribution minus the value of the overall work done without your contribution. So it's essentially your part to the overall work. If that part is less than what you bid for, you're not going to be included in the solution space. If that part is more, then you get that amount. Right? So this makes sure that you don't underbid, because you'll get paid less than you want to, and you don't want that. But it makes sure that you don't overbid, because you're guaranteed to be paid your fair contribution to the goal. But if you overbid, you may not get the deal. Right? So it's not like if you overbid, if you don't overbid, you get too little. It's like if you overbid, you may not get the assignment at all. I hope that makes sense. And there is lots of math to back this up that I don't want to go into. Right?
It basically compares your bid with the average bid of all the others?
No, it compels your bids to your true valuation for the task. Because it's not the average. A regression to the mean would mean I bid the average task. Now, trust me, my time in doing face recognition is probably worth more than the average human being on this earth. I'm not going to do this task for the average payment. And I assume nobody in this room would do it for the average payment.
But it's related to the maximum amount the person that wants the task will pay.
Right. So what we have here, correctly, if you look at this, right, so you do the payout mechanism, and the constraint is, this may fail. That's correct, it may fail. In some cases, the money required is more than what you're willing to pay for. So this is what's happening down here. You add up the costs of the payout, given the assignment xi that we computed in the integer program before, and if it's more, if the cost is less than the budget, you have a way, and if not, you fail. You failed. You can't do this under this fair assumption. So you have to accept the fact that sometimes you can't do it, and that's a message back to the guy or the lady or whoever wants to do this. You need to up the money you're prepared to pay to do this, right? Okay. So we ran two kinds of experiments. The first was a simulation. I'll show you the simulation results. It's 1,000 distinct trials. We had two baseline. One is first completes first served allocation with ex ante defined prices. So this is what's standard, right? You bid for a price and you do first come, first serve on who is doing this. And the second baseline is optimal allocation. So it's using our integer programming, but then do first come defined price payout mechanism. And here is just two very short, interesting things to see. The interesting thing to see is that the budget allocated by the baseline algorithm versus cases that have a feasible solution. Right? They are highly dependent. The two baselines, the less budget you assign, since it's an ex ante fixed, the basis where you find solutions will go down immensely. It's not true for our algorithm. It will always find an optimal solution, and if the budget is sufficient, it will execute it. And now, so what is the fraction of the ones where you can actually execute? And this is what you see here. This is the baseline. So you see the cost of the baseline is obviously, if you pay more, you're going to spend everything. It's going to go down and down and down and down and down and down, right? Because you're not going to pay more, and either it works out or it doesn't work out. Our algorithm, however, so in our allocation, what you can see is the paid budget is the paid out budget is not dependent on how much you're prepared to pay, because it stays relatively stable at the beginning, and only then it declines, right? What's happening here is essentially, even if you are prepared to pay 100%, the optimal payout mechanism by VCG is going to find an optimal price point, and you're not going to pay everything. So this is cheaper in most cases. It will find a better price point, and it will probably make people happier. As well as you will find more solutions in more cases. Okay, let me just kind of very quickly summarize the main ideas, and we have to go on, otherwise somebody will stop me for overrunning my time. So we have a possible payout mechanism that leads to large cost savings in average, but does not directly minimize the requester's cost. It finds more feasible allocations. It increases the requester's utility. It leads to a more efficient allocation, and it offers a principled way for dynamic pricing. Now, I told you about the second experiment we run. We ran this whole thing on Mechanical Turk, and it failed. It failed royally. And we believe the reasons why it failed royally is twofold. First, people on Mechanical Turk, and that is known by now, and there is these websites called Turkanation, and you can look at that, are actually so believing that the people who put jobs in Mechanical Turk are trying to rip them off. They are in a world where this is not the way this world works. It's a kind of race to the bottom pricing world. So it's a matter of mental setup of how this platform works. And secondly, we have this setting where, how shall I put this? It is very difficult to explain to people, Nobel Prize winning technology if they're optimizing to do lots and lots of small tasks and earn 3 cents here and 4 cents here and 3 cents here and 4 cents there. We're currently rerunning this experiment in the lab to see whether on the lab settings we get good results, and then kind of see whether there are other crowdsourcing platforms that are more suitable for this. Okay, so at least in simulations, when we combine integer programming and VCG inspired payout mechanism, we can accomplish a time-constrained crowd that accomplishes tasks at desired quality. By the way, if you were wondering what this is one of our cantons having its annual democratic meeting where they vote on their laws, right? So this is the direct democracy in work, crowds computing at work. Okay, let's go on. Programming language. Otherwise, we'll never end. So how does a social programming language look at? Well, there's two things that I'm trying to give you with here. And one is a notion of process specificity. Programs for computers are usually highly well specified, or have a set of instructions that very well say what's happening next. There are other kind of programs or processes that are unspecified and highly dynamic, and they've usually been modeled in different ways. People have been modeling speech acts or messages and documents or to-do lists, etc. So it's this versus a to-do list. Now, if you think this is a stupid way to program a large bunch of people, it turns out major projects have been coordinated in this way with distributed to-do lists. The bridge over the Öresund between Copenhagen and Sweden was built with a huge to-do list to coordinate all the actors, right? This is not your small normal class project. We're talking about the major bridge, right? So one observation is that human tasks and organizational tasks are really sitting on a wide variety between highly specified and routine and highly unspecified and oftentimes dynamic tasks. And, now let me add one on top of it, oftentimes the tasks while you execute them start moving back and forth between these, right? So let's say you start off with a good plan and it crashes and you're suddenly in unspecified territory and you're redeveloping a plan and you have to move back and forth. There aren't many systems, programming systems that support this. As a matter of fact, I don't know one. Okay, let's go on. Another thing, and this is going to get us into this whole notion of cognitive diversity, is this thing here. So a couple of years ago, I flew to Shanghai, and because I didn't want to bankrupt myself on cell phone charges, I decided I'm going to get a prepaid SIM card. So I went out and typed in GSM SIM card, China, bandwidth of my cell phone, and this is the website it got me to. It's China Mobile, happens to be the largest cell phone provider in the world, or one of the largest cell phone providers, and this was the website. To me, as a typical Westerner, this is not a reliable company, right? I mean, this is bubblegum stuff happening, chewing gums, etc. who is this? I mean, what are they selling? Gambling? Okay, up here on the very top right, there's a tiny button that says English. If you click on this, something miraculous happens. Now that is a company I rely on, right? I mean, you know, moving forward, press releases, focus. I mean, you know, stock quotes. I mean, right? You'd sell your life to those people, right? I mean, that's reliable. Okay. It turns out that our cultural differences are immense in our cognition. They're massive. You know, there's things such as organization of stuff, the way we do it, colors have different meanings, movements, gestures. I mean, you know, there are some gestures that in some country of the Mediterranean are seen as being a compliment, and in others they will get you, you know, killed because you really just insulted someone. So what we proposed, that's Katerina Reinecke, one of my former PhD students, and me, is we proposed this notion of cultural adaptivity. You should build software that automatically adapts to cultural variances. Okay? Sounds simple, right? Well, not quite. If you look at the EC, they could use some translation between cultural differences. And that's only Europe, right? That's supposed to be a simple problem. So we went around and we looked for a simple theory of culture. Okay, we came up with this thing here, which is actually something that was developed very close to here. This guy Hofstede was, I see some people nodding and already smiling. Dutch. He was Dutch, right? He got a contract from IBM. And IBM said, listen, we're doing business in all these countries. We need to teach our managers how to behave differently. Can you give us a simple system by which to assess how to behave in every single country? And he came up with 5 dimensions that define what a culture is like. If you know social scientists, you know this theory cannot be right. Or, even if it is right, it's just incompatible with their view of the world, right? As a matter of fact, this is the most disputed theory in cultural anthropology, probably. Anywhere I go, and cultural anthropologists in the room, I get to say, but this is wrong, and it has been proven in papers so and so and so and so. Yes, but it is the simplest model of culture we could find. And interestingly enough, it's the baseline method that everybody needs to show they're better or worse, because it's so easy to use. So it's the baseline. And the baseline works as follows. There are 5 dimensions. Power distance, which is a question of how hierarchical is a culture. Individualism, is a culture, are people in this culture optimizing their own welfare or the welfare of some kind of collective? Masculinity has nothing to do with testosterone, just has to say how different is the role of women and men in a given society. Uncertainty avoidance, that's obvious. And long-term orientation, that's also obvious. And let's just give you some countries to see the example. This is the United States. Oh, the numbers are I think they're averaged on a world average somewhere, you know, I'm not sure, was it 50 or 75? I don't remember, but it's somewhere in the middle. And then there's below average and line, so they're kind of between 100 and, between 0 and 100, right? So the United States, power distance, no, we're not hierarchical. We're definitely individualistic. I mean, they. Masculinity, you know, somewhat equal. Uncertainty avoidance, yeah. Long-term orientation, what the heck is long-term again? Just to kind of give you the counteraction, China, power distance, very high, right? The hierarchy is important. Individualistic, not really. Masculinity, interestingly enough, very close to the United States. Uncertainty avoidance, trying to avoid uncertainty. Sorry, no, it's very similar to the United States. And long-term orientation, extremely high, right? I mean, you know, we have dynasties of thousands of years. We take the long look. Here is Switzerland. You see that's kind of different than both of them. And the interesting thing is Switzerland doesn't have long-term orientation. Well, there's a very simple reason. It's a very unscientific reason. Hofstede didn't visit Switzerland the second time to make this interview. He did 2 rounds of interviews. He added long-term orientation the second round, so Switzerland was not sampled. Just shows you the quality of this data set. This is Greece. I want to point out uncertainty avoidance. Right, it's like uncertainty, let's insure against everything. Actually, Switzerland also has higher uncertainty avoidance. I think we're one of the most insured countries in terms of, you know, people's personal insurance. We're trying to insure everything. What is this? Oh, this is Japan. Anyway, so what we build is a system that does the following. The system goes out and asks you, where do you currently live? Have you ever lived in an other country before? And if yes, where? And how long have you lived in each of these countries? And now it does something that's probably as inaccurate as possible. It takes the vectors, these 5-dimensional vectors, from each of the countries you've lived in, weights them by the number of years you've lived in, and does a weighted average. And that is you. It's crazy. Exactly. I agree. Now, okay. Now what does it do next? Katerina spent a year and a half of her life of reading every paper published on user interaction and culture, and built a set of rules that will decide if your cultural index is like X, what does it mean on the user interface? And built up a rule base. Okay? So what's happening is this weighted average index gets taken, runs through the rule base, a user interface gets generated, and it gets served to you. Rather than going into the technical details, let me show you some, and anybody who's seen this online is now not allowed to answer. So which country is this? This is a to-do list application. You see the color distribution. There's like the to-dos, today, tomorrow, this week, this month, and we turned everything into English to make this difficult on you. Here you see the projects, so then the kind of topics that you have, and here's some categories. And you see there are icons here, this kind of very beautiful color here. So what country is this? Give me a guess.
Barbie Land.
What?
Barbie Land.
Barbie Land.
Japan?
Korea, Japan. What? India.
China.
China. Okay, this is South Korea.
South Korea.
And because you mentioned some countries before, what is this? I mean, you see the complete difference, right? Still icons, but there's very clear lines here. The colors are all subdued. Icons, large press, the categories here, the project. There's a wizard here. There wasn't a wizard before that will guide you through the steps. Germany. German, right. Sorry, this is Japan. This is Japan. Right? These are next to each other, these two countries. It's very different. Very, very different. Okay, what's this? This is China. You talked before about China. This is China. Now look at the difference again, right? I mean, we especially took these 3 countries because we're all kind of Westerners and we think it's all the same. Sorry, but they're not. But they are very different. The colors are different. The ordering is different, right? That's just the way this is ordered. You see the size of the buttons varies. The color scheme is very different. And actually, let me just add you one, because you talked before about the Germans. I didn't bring you Germany. I should bring you Germany. And actually, I should bring you Belgium. But probably there would be argument whether I should have the Wallonian or the Vlaams version, right? So this is Switzerland. And now, interestingly enough, if you look at it from afar, it is very similar to the Japanese design model. But it doesn't have these big icons. It's small, it's tiny, it's very kind of, fine. But the color scheme is also not very different to this one. There are some sizable differences here. As a matter of fact, I urge you to go to our website at the University of Zurich, and you will see a lot of this in place, very tiny print. We had to fight with our university for like a decade to get a logo in place that's actually visible. That doesn't have like fine print, fine. I mean, this is very Swiss. Okay? Okay, now, let me give you some evidence that this actually works. We ran some experiments. We ran 2 sets of experiments. The one that I'm going to show you here is a test on efficiency and satisfaction. We gave this to 41 participants from 25 different nationalities. Age range is 20 to 36. 25 of which were female, with a high education level. And they were regular computer users. And we asked them to run a certain set of these to-do list applications in 2 different versions. On the one side, they took the baseline version. Sorry, I display, this is not the right baseline version. The baseline version is the US West Coast, right? Sorry, because that's where most of the software gets developed. So that was our baseline. And they also had to use their personal ones, and what we obviously did is some people start with the US baseline, others with their personal one, and others the opposite. And I'm just going to give you a set of metrics that we found to kind of give you a feeling for it. The whole experiment is a paper in itself, and it takes a lot of time. The average completion time is significantly lower than in the US baseline for the personalized one. The average number of clicks is significantly lower than the US baseline. The average number of errors is immensely significantly lower than on the US baseline. Right? There's something similar on how aesthetic people find their baseline. And trust me, I don't personally, and I hope I didn't find some of these images before very aesthetic, but the people from those countries, and we didn't just run this in Switzerland, just to make this clear, right? We ran it in multiple countries in the world. Katerina was teaching a course in Africa, so she ran the experiments there, etc., etc. Okay. But this is still a small number. Let me give you evidence from larger numbers. How many of you use doodles to find? Because this happens to be a Swiss company. Almost nobody knows this. There's a bunch of guys in a garage who started this company in Zurich, and we got the data on 1.6 million doodle polls, and we analyzed them by countries. Now, when you do doodle polls, there are a bunch of decisions you face, like, what have others chosen? What time suits me best? Should I disclose less convenient times, or am I very egoistic? What will they think of me if I make this choice? Or will they think I've got nothing else to do if I disclose too many options? Okay. Now, individualism obviously influences decision-making in such things. So we have things such as autonomous decision-making here in Europe versus confident in its own decision-making here versus in more collective decision-making and sharing responsibility. I need to wait for certain people to make the decision and then I fall in line. So we took 1.5 million doodle polls in 211 countries, sorted them by GDP and population data, and used a bunch of metrics. And we find differences that are culturally significant on, people use open polls or hidden polls? You probably have never seen a hidden poll. It's the polls where you don't see what other people vote. We see differences in consensus and friction on one end of the spectrum of individualism towards the other end of the spectrum of individualism, etc., etc. I could go on forever about this, and I won't in the interest of time. Let me give you a last piece of evidence. Katerina and a colleague of her did an analysis of MOOCs on edX, and she found that these guys up here and these guys down here, so here we have India, Pakistan, Kenya, and Nigeria, and up here is Sweden, Poland, Hungary, etc., are very, very different in their way to navigate the MOOC. These guys here optimize towards, they look at what an assignment is, and then they go and look in the MOOC what they need to know to follow the assignment. These guys over here, they follow the linear structure of the course, and whenever they need to, they do the task. Right? So we see this again and again and again. So, what am I trying to tell you? I'm trying to tell you that cultural adaptivity, so adaptivity based on cognitive difference, is possible. We have at least seen one of them. We need to build this into programming languages in some way to pick the best people for a given task. And it is a fact that it happens. It's not like the internet has equalized us all, even with such a coarse-grained thing as culture. Okay, last thing. I'm almost done. It's the fastest one because I don't have that much evidence to show you. Software engineering. How can we do software engineering? It turns out that this is the Congress information, the US Congress, where they actually did societal software engineering. They decided on how the Constitution should be, right? So how can we do this? Let me get you and talk to you about how can you deal with error diversity in this context. How can we control for error with software engineering approaches in programming the crowd? Almost done. Okay. So in 1999, we wrote this paper that said, if you look at processes, what you really have is a bunch of ways of doing things. So you have some abstract process. Here is hiring a person. You need to identify your staffing needs, identify potential sources, select human resources, make offer, and enroll the employees. And each of these things has a bunch of different ways to do this. And what you really have is a huge design space of possible ways to do this. For example, select human resources. Just to pick up one, the Swiss Army has a very easy way to select human resources. They hire everybody, and they kick out the ones that don't perform. And then they need to pay, and otherwise there is an incentive not to perform. But they actually pay up to 3% of their net income in kind of I don't serve in the army taxes. But other people do different things. I believe it was BMW who, for mid-range managers for a while, put them in an office for a day and saw how they acted in the environment of an office. I think Marriott had an online simulation you had to play through in order to essentially get to submit your, it's kind of qualification test, an online qualification test. So there is many ways of doing this. So you can see how this opens up a design space. So let's put this into the realm of social computation. So we built a system called Crowdland, and we built a program that translates books. How do we do this? We take the text, we chop it up into its paragraphs, and then take each of these paragraphs, chop it up into its sentences. Then each of these sentences gets sent into the best automatic translation system known to mankind called Google Translate, which sometimes gives very entertaining results. We then take those translations, and here is where the human aspect of the social program starts. We take these things. I'm faster than the simulation. We take this and give this a bunch of people to rewrite, and then we take a bunch of people to decide which of those rewrites is the best rewrites. Okay? For example, by voting. We now have good sentences that are well translated. Now, those are all monolingual. They don't know the original thing. We put this together into paragraphs. We do the same thing for the paragraphs. We let people improve them, and then let voting happen on which one is the best improvement, or some sort of collective selection procedure. Then we do the same thing for grammar. We put the whole text back together again. And what we essentially have is a process that uses monolingual translators to translate large numbers of text in a time. Okay, so this is not software engineering yet. The software engineering part comes, and now you'll see lots of boxes and arrows, and I don't expect you to understand them. Here is this process in boxes and arrows. Each of these things is one of the human computation tasks, and each of these human computation tasks can be accomplished with this, with this, with this, and with that. Those are different coordination mechanisms for human computation. This is Bernstein's et al., Michael Bernstein's et al., find, fix, verify mechanism. It's kind of an iteration where you find problems, you have some people who find the problem, you have other people who try and fix it, and then you have yet other people to verify whether the fix is any good. Right? So it's kind of an iterative process. And there is others, there is voting, there's just a bunch of these processes. And the beauty of a social brain operating system, environment, etc., is you can generate your whole design space and just run them all. And that's what we did. And just to kind of show you the results, is you see here 4 different versions. The baseline is just Google Translate by itself. The reference is a man-made translation, right? So a professional translation. And these things are some combinations that are coded up there. And we don't have here. Oh, I just give you 2 here. And these are grades given by the crowd to the final thing, or by specialists, by professionals. And you can see that these things they're not as good as the professional translation. There's no question, right? If you read Milan Kundera, you don't want it to be translated by the crowd. But nonetheless, here is what the specialists, the professionals tell us about these translations. The baseline, this is nonsensical, tenses are a big issue here, and therefore makes the sense very difficult to understand, versus the best performing algorithm of ours. This would be fine, except for 2 places that incorrectly use the relative clause. You know what? The kinds of things I wanted to read already in my life, if it's 2 incorrect relative clauses that are my problem, I don't have problems. Okay, so just to kind of see how this scales, we took John Grisham's The Client in German and let it translate to English, and this was accomplished in 4 hours for $67. Now this is not the version of John Grisham's The Client you want to read in English, because it's not an enjoyable read, but it's a read where you know what happened in the story and how it happened, and you know all the details you need to know. Good enough for 90% of the things you need to do. Okay? So this was the 3rd thing I was bringing up. Okay. I'm getting to a close. I believe that our world has a bunch of threats that really threaten its existence in the future. On the other hand, it has a whole bunch of opportunities that we have, be it from machines, be it from robots, be it from sciences, that allow us to address it. My personal belief, and the belief of my co-authors of this paper, Mark Klein and Tom Malone, is that our ability to conquer these problems are going to depend on how well we master the art of programming the global brain. Thank you very much.
you.